So, welcome everyone to the 11th lecture of XML and Web Technologies. So today we will having a guest lecture. So we are very happy that we have Angelo Salatino from the Open University in the UK. He's a member of the Knowledge Media Institute, and he's working generally in the field so-called science of science. So he has worked before on semantic web technologies and knowledge discovery techniques. And today he will be talking about scientific knowledge graphs. And we are very happy to have him. Angelo and I have been working together in the recent years, and we have some common interests, and we have joined forces. And I'm very happy that he has accepted this invitation. So without further ado, let's virtually welcome Angelo, and I will leave the floor to you. Thank you, Angelo.
Thanks, Dimitris. I hope you hear me well and you see me as well, right? Okay, so I'm going to start sharing my screen. Okay, perfect. You can all see my screen, right? Let me start sharing. Let me start going in presentation mode. Okay, you should see my screen like in full presentation mode, right? At the moment.
Excellent. Yeah.
Okay, perfect. So yeah, thank you, Dimitris, for inviting me, and thank you for the nice introduction. So yes, today I will be talking to you about scientific knowledge graph. I will provide an overview on scientific knowledge graph, and in particular, why they are useful for, what they are, how they are built, and potentially what we can do with them, and all these kind of things. So just before starting, I would like to, so that you get attuned to my accent, because I have a good strong accent, Italian accent. I will start talking about a little bit about myself before starting going into the lecture. So I am Angelo Salatino, and as Dimitris has already mentioned, I work at the Open University in the UK, and mainly I am a research associate and an associate lecturer there. And my research interests are new technologies for classifying scientific papers according to their relevant research topics, and how the research output of academia fosters innovation in industry. This means that the main activities that I do are mainly based in, given a document, identifying what are the main topics that are discussed within these documents, so that we can classify them, we can categorize them according to their subjects. And also, one of the main activities that I do is understanding how knowledge flows between academia and industry, and vice versa, because this is important to understand and support policymakers in driving fundings. I work for the Scheme3 team, which stands for Scholarly Knowledge, Modeling, Mining, and Sense Making. And what we do is we leverage large-scale data mining, semantic technology, machine learning, and visual analytics to extract meaning from scholarly data and shed light on the research dynamic. What's in today's agenda? So, as I mentioned at the beginning, we will be talking about scientific knowledge graph under several perspectives. Again, why we need them, what they are, and how we can use them. And then I will talk about AIDA, which is a specific use case. It's a specific scientific knowledge graph that I've been building with my team. I will show what we can do with AIDA, what is the potential that this knowledge graph opens up, and some practical tests. So let's start with why we need scientific knowledge graphs, and to understand a little bit better why we need this. Dimitris has already mentioned that I work in the field of science of science, and indeed, because of this field, this recently emerged field that we have now, the scientific knowledge graph come quite handy to support this field. But let's understand what is it exactly. There is one particular paper that was published in 2018, and actually, before actually going into the definition, I want you to focus for a second on this picture on the top. As you can see, there are scientists observing over other scientists, and the name suggests exactly that. So we do science over science. We tend to understand how science evolves, how science proceeds towards its goal. And indeed, the definition that has been given by this paper is that the science of science places the practice of science itself under the microscope, leading to a quantitative understanding of the genesis of scientific discovery, creativity, and practice, and developing tools and policies aimed at accelerating scientific progress. What this means is that we take science, we analyze it, we put it under the microscope using this quote words, and in a quantitative way, so through numbers, we understand how discoveries are made, how creativity is, it's playing its role, and all practice and tools that have been using in science, because the goal of this science of science discipline is accelerating the progress of science. And there is another book that was recently published, I think less than 2 months ago, at the end of March, which is called The Science of Science by Dashun Wang and Barabasi. And the way the science of science is defined here is it's a multidisciplinary field which helps us to understand in a quantitative fashion the evolution of science. And here again, I want to stress, this is why I underlined it, the word quantitative, because quantitative usually means with numbers. So we define metrics, and through these metrics we assess things and we evaluate things. And then this book keeps going on with, this is possible by capitalizing on large amount of data scientists producing research article, preprints, grant proposal, and patents. So all these documents can support this field, in understanding and measuring this field. And there is a little spoiler here that scientific knowledge graphs come quite handy for structuring and collecting such data. So all research articles, papers, preprints, grants, and patents can be structured within this knowledge graph, scientific knowledge graph, to support this assessment. So this is the why we need them. But now let's get into the scientific knowledge graph. So I want to start with research dissemination, which is an important aspect of what we do as researchers. And indeed, when we do research, we start off by understanding what are the problems, or what are the actual world problems, or what are the research gaps. And then what we do, we design experiments, we assess them, we evaluate them, and then as soon as we get something tangible, a tangible result that is worth being published, we publish it. And this is published through research publication. And many people can think that actually research publication is the atomical structure of knowledge, because you have one entity, which is the research paper, and that contains knowledge, and that's atomical. But actually, from our perspective, the research paper is not atomical at all, because it contains a lot of information that can be extracted. For example, this is how we interpret a research paper. People that typically work with scientific knowledge graphs interpret a research paper. So there is a paper at the center of everything here, and then you have all sorts of information. So the atomic information here are the single authors, the single affiliations, where this paper has been published, so the venue, whether it's a conference or a journal, the keywords, or the citation, or the references, title and abstract. Those are all possible information that we can extract from those manuscripts that I just showed. But this is just one single view. It's just a very narrow view on one paper in particular. But how does it change when we take into account several papers. And this is how it changed. I mean, this picture is pretty ugly, I must admit, but I couldn't find a better way of representing it. But what you are seeing here is just a network of paper. Each icon here is a document, and they're all interlinked between each other. And all these papers refer to other entities, authors, conferences, as I mentioned before. So for example, this paper here and this paper here that has got as entities me, and my colleagues. So for example, those are both papers that have been written by myself. And also you can imagine how this like very large structure gets interlinked in all possible ways. So it resembles mostly a graph. So you start seeing how the graph come quite handy for structuring and representing this kind of data. But what happens if, for example, we include other entities like funders, institutions, projects, and community? It becomes even more complex. You have all sorts of entities all interconnected between each other. So here, what I want to do, I mean, and you have like several institutions working on a project, several people. So you can build interconnection within this network, not only referring people to papers, but people to other people because they collaborated or because they shared a project, also like funders because they funded a particular project. So this building a knowledge graph is actually limited to the imagination of the person who builds it, potentially. So there is no limit on what kind of information it can store. So here I want to stress that scientific knowledge graphs are a way for representing scholarly knowledge in a structured, interlinked, and semantically rich manner. So potentially all links have a meaning, they are all entities are interlinked, and there is structure in there. So this is the real power of scientific knowledge graphs. But now let's get into the definition of scientific knowledge, because what we have been seeing so far is just showcasing and examples. But let's get into the real like gist of it. So given a set of entities, what is the definition of a scientific knowledge graph? Given a set of entities which can be literally considered as nodes. So of course a network has got nodes and relations. So entities are nodes, and given a set of relations R, a scientific knowledge graph is a directed multi-relational graph G that comprises triple subject, predicate, and object, and it is a subset of a cross product between all possible edges, relations, and edges. So given all possible combination of subject, predicate, and object, the scientific knowledge graph is going to be a subset of that cross product between all these things. And here, another thing that I want to mention is that nodes, which are entities, and relationship, which are edges, are have got a well-defined meaning. So, for example, here there is again a paper at the center of everything, and then there is title. So the relationship has a meaning. This relationship means that this paper here, 635219, has got title, detection, analysis, and so on. Then has got as author myself, that I work at the Open University. There is also my colleague Francesco that works as well at the Open University, and then there is another colleague of mine, Andrea, that works for the Italian Research Council. So you can see how the network actually has got the potential to structure all this kind of data, and in an interlinked manner, also in a semantic way, semantically rich way. Okay, how do we represent? Because so far we have been seeing like pictures of a network, but unfortunately within files we don't represent picture, we represent data. And actually I am assuming that you know RDF, because this course is about web technologies. But just to have a brief reminder, so one way of representing graph is through RDF, which is the acronym of Resource Description Framework. And RDF is a standard for data interchange that is used for representing highly interconnected data. And if each statement in RDF is a triple consisting of basically resources where every resource is in a URI, and the data in RDF allows information to be easily identified, disambiguated, and interconnected. And here there is an example. I mean, this is just a toy example, but here there is an example of how we can structure the picture that I showed to you before. So again, there is a paper within a URI that has got a title. So also relationships have got a URI. The only exception is for objects. Objects can be either URI or literals, because in this case, for example, the title is a literal. It's just a string. I don't have to. There is no need for creating a URI also for the title. The same is also for the abstract, also for the keywords. But for example, when we have the information about myself as author, so this paper has got author, me, then the URI can be quite handy, because then what happens is that there can be other papers within this knowledge graph that have got me as an author, so we can disambiguate using the same URI, URI Angelo Salatino. What happens is that we can create a relationship between those two papers, having me as an author. So in this case, having the author as an URI, it's kind of important rather than having me as a literal. And yeah, that's basically it for it. And however, one thing is, not all scientific knowledge graphs are published in RDF. For example, in Dimensions, which is one of the main provider of scientific knowledge graphs, because I will show to you in a bit that we don't have to do the work of creating them. There are companies, or there are like agencies that do that for us. So we can simply download them and then we can operate with them. But anyway, there are like companies like Dimensions that does not release their scientific knowledge graph in RDF, but it does in JSON, which can potentially be translated quite easily in RDF. But for the sake of simplicity, they prefer to release it in JSON, because in their technologies, it's easier to interoperate using JSON. So RDF is used, but it's not the only format that is used. I mean, even Microsoft uses, for example, table separated values. So it's just to give examples, but RDF is the best way to represent data. Anyway, let's move instead to again data providers, because or actually data sets, because as I mentioned to you before, we don't have to build them. Most of them are already built. Some of them needs refinement, but the core is already kind of made. So there are a lot of scholarly datasets, big scholarly datasets. Here, big scholarly datasets or scientific knowledge graphs are kind of equivalent in the way I am telling you the things. So it's the same. I will use like in the same way. So some of them are Web of Science. There is Web of Science, which is actually the oldest one, the most, the oldest one. Actually, it was built more than 70. It was they started building it more than 75 years ago. I think in 1963, 1964, something around that. I don't remember precisely the year, but that is the period. Because there was a researcher, Eugene Garfield, that felt the need of starting assessing science, and what we did is started this initiative, like gathering citation data, in order to and actually from that it came out also the impact factor. I don't know whether you are familiar with it, but the impact factor, it's one index of assessing journal, whether a journal it's a good one. And many people use it. Actually, they misuse it. But anyway, I don't want to spend too much word about it, too many words about it. But the impact factor is one way of assessing journals, whether it's considered good or not. And it was developed by the same person that developed Web of Science. He needed a way to develop a metric, and to do that, It needed data. So that's why I started building Web of Science. The reply of Web of Science, the commercial reply of Web of Science was Scopus, which was built only after 40 years in 2004. So between 64 and 2000, Web of Science was the dominant scholarly knowledge graph that was available. Then Scopus arrived, and then this this sparked like a movement in which many people were starting gathering scholarly data, like Google Scholar, Microsoft Academic Graph, PubMed, then Dimensions, Semantic Scholar, DBLP, and I don't want to mention all of them, but the list that you're seeing here, actually I want to mention the last one, which is AIDA, which is the one that we built as team, and I'm going to present it a little bit later in this lecture. But anyway, what I want to say is that this list is far from being exhaustive. Like, there are so many out there, and every year there are new other ones coming out. So this world is becoming very intense in terms of existing datasets. Now, all these datasets have got differences, because you may wonder why we need all of these datasets, all these big scholar datasets. There is no sense. It's because they have differences, and these differences span across several features. And the first one that I want to talk to you about is size. So this is what you see on the right hand side is a comparison between 5 different datasets: Scopus, Web of Science, Dimensions, Crossref, and Microsoft Academic Graph. And as you can see, this is the comparison in terms of size and how they overlap. So you can see that, for example, Microsoft Academic Graph, this researcher in this analysis, they compared only 73 million papers, 73 million documents. But actually, I can assure you that to this date, Microsoft Academic Graph has got 258 million. So we are talking about more than 3 times that amount there. And you can imagine how massive is that. And other datasets can be smaller because they don't include papers for several reasons. That can be either political, because, for example, they don't include paper from a journal that they consider it's not good enough, or, for example, they don't have the power to include all these papers that are missing, because, for example, they don't find it, they're scrapers, they don't find it, or they don't have the manpower to include them. Because one thing that I want to mention here is that research papers today are published very quickly, so it's very hard to keep up with the pace of the publishing industry. Another difference is the scope. So, for example, MAG, Dimensions, Scopus, Web of Science cover or tend to cover all areas of science, which is computer science, medicine, art, history, philosophy, any kind of science. DBLP covers computer science, PubMed covers only medicine, and Semantic Scholar covers computer science and medicine. So another way in which we can compare these datasets, it's through their scope, what kind of discipline they're able to cover. Another way is quality. What does it mean, quality? It means having clean data or removing duplicates, because the same document can appear on multiple places on the web, because one operation that some companies do is scraping in the web. But, for example, my papers can be on my website, on my university website, and also on the journal website where I published. So there are 3 copies of my paper. So if this company is not very good in disambiguating the same paper, so saying, okay, these are 3 versions of the same item, they will have 3 papers about me, but it's actually wrong. So it's only 1 paper. So then there is also disambiguating authors, disambiguating affiliation, and disambiguating references, because authors is also a problem. There can be several John Smiths, for example, okay, there is John Smith at the Open University, there is John Smith at the University, Stanford University, or New York Central University. And now, what is this John Smith that we are talking about? Is that one, or that one? So it's important also to be good in disambiguating. So the problem is that there are data sets that have got several mistakes. And in general, what I can tell you is that Web of Science and Scopus tend to be really, really good in terms of quality compared to MAG. And indeed, they have high quality data. Instead, MAG can have some errors. Oops. Yes. And this is another thing that I want to mention, is that one problematic in extracting information from papers is the extraction information from papers, because as you can see here, there are 5 examples of published papers. So imagine I wanted to extract information from these papers, and you can see there are several formats, like several templates. So I have to build, and this is just 5 of them, but you can imagine there are hundreds of them, like thousands of them. Each journal has got its own template. So this is just to give you a little bit of understanding on how complex can get things when I want to extract information from PDFs. Because, for example, the authors for this paper are here, the authors from these papers are here, they are here, but the authors of these papers, for example, are here, or so the information can be really hard to grasp, because, for example, there are other information in this column here. So if the machine is not properly trained, so the automatic tool is not properly trained to extract those information, it can make a lot of mistakes. There are automatic tools like Grobid, which is quite famous in this field, that can extract this information. It works on neural networks, like automatic or machine learning approach, that is able to extract information from paper. You give the PDF, it comes out with the metadata, but still it can make some mistake, because eventually it's an automatic tool. It's not a person. I mean, people make mistake. You cannot imagine how machine tend to make mistake as well. And indeed, this is another issue. This is another way of comparing. It's indexing versus scraping. Some datasets tend to index stuff. So there is Web of Science, Scopus, PubMed, which are manually curated. So what happens is that, okay, there is a new issue about a journal. So there is a way in which people have set up, there is a way in which people, or like machine, add this paper in a controlled manner, in a curated way, so that the metadata that we push within those datasets are cleaned. On the other hand, MAG, Dimensions, Google Scholar scrape the web, so they scrape journal website and PDF. And as I mentioned to you before, there can be issues when you scrape PDF or journal websites. And this is just to give you an example. This is a paper that in the right bottom, this is a paper that I published in 2015. And what happens is that I am affiliated with Instituto Politécnico Nacional, which is an institute in Mexico. And I can assure you that I've never worked for Mexico yet. It can happen in the future, but I never worked. So you can see that there is a clear mistake. I was working for a Polytechnic university in Italy, but that Polytechnic university has been confused between Instituto Politécnico Nacional. And so this is just to give an example how things can get wrong. Comprehensiveness. This is another way of comparing datasets. So here there is a table that compares datasets across of what kind of features they have. So the X, it means that that kind of information is available. For each paper in MAG, we have title, ID, abstract, year, and so on. We don't have author keywords, which instead are within Scopus and Web of Science. So for the conferences and journal in Semantic Scholar, we have partial information, which means that the information is there, but needs to be reworked a little bit if we want to make sense of that information. So this is just like a comparison on a small bunch of features, but this is not the limit of the kind of features we can have in a dataset. And indeed, for example, in Scopus, we have a lot of information. So we have abbreviated source title, article number, authors, chemical name, cited background. There are like a lot of information that we can use for our analysis. So this analysis that I show here is just an analysis that can compare fairly all datasets on a bunch of information, but that list is not exhaustive. And I mean, this is the minimal list, but as soon as we start enlarging this, there are a lot of differences between each dataset, because each dataset tend to differentiate in terms of comprehensiveness. The other feature that we can use to compare datasets is whether they have a sort of integration with other data sources. For example, there is the Open Academic Graph that integrates together, maps together MAG and ARNet-Miner. And the OpenAir, for example, Research Graph integrates Crossref, Unpaywall, ORCID, and MAG. And AIDA instead integrates MAG, GridID, DBpedia, and CSO, which I will show it to you a little bit. Another difference that I mentioned to you before is also the format. So Dimension, PubMed, Semantic Scholar, Crossref are distributed in JSON because it's easy to manipulate, it's easy to integrate, but as I mentioned to you before, the richness comes with RDF, because links in RDF can be also represented and have a meaning, and then the entities have got their own information and so on. Web of Science and MAG are distributing tab separated values. MAG Knowledge Graph, which is the semantic web version of MAG, it's in RDF, of course. Then there is AIDA, Scholarly Data, Open Citations, which are in RDF, and DBLP, it's in XML. Another way to compare dataset, and this is the last one that I'm going to present, it's license, because some dataset comes for free with a license. You can download it, you can use it, as long as, for example, you respect the license. So, for example, Semantic Scholar, it can be downloaded for free. It has got an ODC by license, so whatever things you do, you need to mention them, which is fair, I think. Dimension is free if you're a scholar and has got some copyright. Then MAG has a manageable fee. You only pay $50 for downloading it, but the dataset itself is free. So what you are paying instead is the bandwidth for moving MAG from their server, so Azure servers, to your computer. So that is the fee of downloading it. Otherwise, the MAG dataset is completely free. The ones that are very costly instead is Scopus or Web of Science, because of course you need to pay human labor. So there are people that curate this dataset, and you have to pay them. Not available to buy, not available to download, it's Google Scholar. There is no way you can use it. If you try to scrape them, you will see police under your door. I'm kidding, of course, but they won't allow you, because they are very good in determining when someone is trying to steal their data. They have very nice algorithms. People tried and they failed, so there's no point of doing it. So now that I've given you a very wide overview on scientific knowledge graph, I can move into AIDA, which stands for Academic Industry Dynamics Knowledge Graphs. So AIDA is, as the word says, a knowledge graph that consists of 14 million papers and 8 million patents that have been annotated with research topics from the Computer Science Ontology. So each document, paper or patent, have got an indication of what are the subjects in computer science that are discussed within this document. So if a paper is about machine learning, or if a paper is about artificial intelligence, or if a paper is about semantic web, or semantic technologies, or web technologies, all this kind of information. Then what happens, then what we have as well is out of these 14 million papers and 8 million patents, 4 million papers and 5 million patents have been classified according to the type of author affiliation. So whether this paper has been written by academic institution, industry, or collaborative. So whether I collaborated with a researcher in an industry, so our work is going to be collaborative because it's between academia and industry. And then these papers, in case were either collaborative or industrial, were also annotated according to 66 industrial sectors from the Industrial Sector Ontology. So, for example, if a paper was being written by IBM, for example, because IBM is a very active company in the research, and if a paper was written by IBM, all the papers written by IBM would be tagged with semiconductors, because IBM has been working a lot with semiconductors, also with artificial intelligence, because let's not forget that IBM has been doing the Watson thing that won the Jeopardy game 20 years ago, I think, something like that. Anyway, so they work intensively also in artificial intelligence. So all papers of companies are also tagged with this industrial sector. They can be telecommunication, aerospace, or artificial intelligence, or also in oil industry, or you can potentially imagine all sorts of industrial sectors. And then this is released as a RDF graph that is available either via Sparkle through our Triple Store, through our Sparkle endpoint, or as a dump. You download it, you put it in your Triple Store, and you can do whatever you want. Now, how it is built, because this is an interesting aspect, just to still stress on the fact that how we can learn more about scientific knowledge graphs. So the first thing is, this is the pipeline typically. What we do is that we collect the research papers from Microsoft Academic Graph and patents from Dimensions, because Microsoft Academic Graph doesn't have patents, but Dimension has them. Then we filter documents, because again, we wanted to analyze papers and patents in the field of computer science. So there is no point, because Microsoft Academic Graph, as I mentioned to you before, covers all areas of science. So it is important to filter here to not process useless document, because we won't be able to infer topics out of it. Then we extracted topics, and we designed, I mean, it's a tool that I designed a couple of years ago, which is called the CSO classifier, and which annotates papers and patents according to the computer science ontology. The computer science ontology is, you can think of it as a controlled vocabulary. So in this vocabulary, there is the list of all possible topics in computer science that can be potentially inferred. So this CSO classifier, what it does is look at the content of the paper or the patent, and then mapping with the topic within the computer science ontology. And actually, I want you to beg to not lose the focus about this, because I want to spend about the AIDA pipeline, because I want to spend a little bit more time on the CSO classifier. We will come back to this again, but here I want to spend like really 2 to 3 minutes about talking about the CSO classifier, because I think it's really important. And so the CSO classifier, it's an unsupervised approach that takes in input paper metadata or patent metadata, so title, abstract, and keywords. And as I showed you before, title, abstract, and keywords were kind of available in Microsoft, except the keywords, but still with title and abstract, we can do the same, we can do the process. So this algorithm takes in input title, abstract, and keywords. And then what it does, it consists of 3 modules, the semantic module, syntactic module, semantic module, and then a post-processing module, and annotates the topic that are available within the computer science ontology. So very briefly, the syntactic module, as the term suggests, it's a module, it's like a piece of software that goes into the text and identifies topics that are available in the text, that are explicitly mentioned in the text. So that's why it's a syntactic match. So what it does is parses the text, and then it splits in unigrams, so parts of text that consist of 1 word, 2 words, and 3 words, and then it maps them. It goes into the controlled vocabulary and looks for whether this 1 word, 2 word, and 3 words coming from the paper are in the controlled vocabulary. If they are there, basically it flags this topic as an important topic of this paper, as a relevant topic of this paper. And there are several heuristics that we can use. And in particular, we used the Levenstein similarity. The Levenstein similarity is just a string similarity. It takes two strings, it compares them, and gives a value. So if, for example, I give, I don't know, an example, string 1 and string 2, it's going to return the level of similarity. And if this similarity goes above a certain threshold, we can consider these words similar. In this particular case, I used the threshold of 0.94 because this threshold is highly enough that we can consider that words as topic, and that 0.94 is not that high because the max value is 1 and the minimum value is 0, but we did not set to 1 because there can be several nuances of the word, for example, because for example, if there is database in the text, but in the ontology there is databases, I want to match that. So I want to be sure that I am matching it. So then there is also hyphens, for example, knowledge-based system and knowledge-based system. So having a threshold of 0.94 allows us to identifying very similar strings that really represent topics, but having a certain degree of relax, because it also allows us to identify whether there is an American or a British spelling. For example, data visualization with a S or data visualization with a Z. So with this trick, we are able to identify data visualization as a topic. How the semantic module works instead? The semantic module captures the semantic of words, so it doesn't work on a syntactic level anymore. We go one level above, it works on a semantic layer. And what we do is, again, we process the document, and then for each relevant word, we go into this word embedding model. Now, I'm not sure you know what exactly is a word embedding model. I'm going to explain it in just 2 seconds, very briefly, but just to give you an understanding of what exactly it does. But what it does, what we do in this module is that we go into this module, we have a word, we go into this module and we retrieve the similar words, because this module captures the semantic of words. So for example, if I am talking about house, okay, and I go into the model, it's gonna tell me one possible semantic related word is gonna be home, because house and home are different versions of the same entity or the same thing, or desk or table. There will be clear examples in just a few slides. So then for each word, we select the relevant words and we check within whether these relevant words that we extracted from the model, so these similar words, are within the, I need to rush a little bit, are within the computer science model, computer science ontology. How does the word embedding model? The word embedding model is a machine learning approach that, given a word, it assigns numbers. So it gives, and then with these numbers, we can do arithmetic operation, basically. So imagine here, I have the words king, queen, woman, and man. I am associating to each word an array of numbers. And these numbers can be, now in this case, there are just 2, but this number in real world can be from 265 up to 1,000. I've seen models that have got a word represented by 1,000 of these numbers. And then we can do all sorts of arithmetical things to identify whether 2 words are semantically related. And one of them is exactly the cosine similarity. So we can do the cosine similarity between king and queen and see how far those 2 arrays are between themselves. Now, these arrays can be represented in multidimensional Euclidean space. So for example, here you can see a 3-dimensional space in which there is king, queen, man, and woman. And one cool thing that we can do is a mathematical operation. So if from king, I am like, consider this place, I am in king, and I take distance between man and woman, which is this distance here, and I subtract it from king, sorry, and I sum it to king, I get to queen. So this is the operation. If I take king and I add the distance between woman and man, okay, I get queen. So this is the semantic relationship that we can extract. This is the semantic power that this model has. And another kind of example is verb tenses. So we can move from the ing form to the past form. So if I want to know the past form of the verb swimming, I can simply calculate the distance between walking and walked, and I can add it to swimming to get to swim. It's the same also for the capitals. You have countries and capitals. They tend to have the same distance among nodes. So this is the power of word embedding model. And we are able to identify synonyms that have got high cosine similarity. So potentially two words that are considered synonyms tend to be very close to each other. So an high cosine similarity will tell me that house is related to home. This is just an example. So again, what we do is that we train the word-to-vec model, we get into the model. So here there is an example. There is the web application word. We go into the model, and then we tell to the model, can you tell me the top 10 similar words? And the top 10 similar words is web applications, web with the hyphen application, browser, web service, browser-based, web portal. So those are the top 10 related words with the word web application. So, and here I have also the score. So it's telling me how similar in terms of cosine similarity are those two words, the array of those two words are. And then what I do is that once I gather these top 10 similar words, I look into this in this computer science ontology, and I say, and I check whether those are topics or not. And if they are topics, they are considered relevant topics for the that document, either paper or patent. Then what we do is that since the number of topics returned by word embedding model is very high, we filter them. I don't want to dive into much details also because the time is running and I have other slides to show to you. But then what we do in the post-processing is that we join the forces of the syntactic module and the semantic module, because both syntactic and semantic module have got a voice towards understanding what are the topics in this paper or in this patent. And then we do another thing, which is the semantic enhancement. So because the ontology is not only a controlled vocabulary, but has also semantic relationship between topics. So what we do is that we include syntactic and semantic, but we include also the broader topics. So for example, if the classifier has been inferring machine learning, I also add artificial intelligence, because the artificial intelligence is a broader topic of machine learning, because a paper talking about machine learning is most certainly about artificial intelligence too. And this allows us to get a broader context of the paper, because as I mentioned, if I am talking about machine learning, I'm also talking about artificial intelligence. Now, this is the CSO classifier. We take our patents and papers, we classify and we extract topic. Then what we do is we extract affiliation types and industry sectors, because we want to annotate whether a paper or a patent has been published within academia or industry, or has been a collaborative effort, and whether it has been, and if it has been an industrial paper, we want to understand what are the industrial sector of this paper. So to do this, we use GRID. GRID is a global research identifier, and here there is an example of the Université Libre de Bruxelles. There is the identifier. So each academic institution, either company, government, hospitals, or university, or companies, have got an ID. I've got their own ID, and with their ID comes with a lot of information. So, for example, I can see that your university is an education institution, so it's an academic institution. It's not governmental. It's not a company, an industrial institution, but it's an academic institution. It has been established in 1834, and then there are other information that are connected to other services like Wikipedia, Wikidata, Crossref, and the website of your university, and so on. So thanks to Grid ID, we can understand whether an affiliation is education or company. Then what we do, we take the Wikipedia URL and we query DBpedia. DBpedia, Wikipedia are the same thing. One is the textual version. DBpedia is the RDF version of Wikipedia. So we go to DBpedia because the URL is the same. We go to DBpedia, and if it is an industrial thing, industrial institution, we get the type of institution. Now, DBpedia is very noisy. It has got like more than 600 kind of types. So it's very hard to make sense of all this bunch of types because there are a lot. So what we can do is that mapping them to a controlled vocabulary of industrial sectors. So we map them to those 66 industrial sectors that are within the INDUSO. So they are a limited number, but group together all the other that are on DBpedia. So this is a way for us to cluster or to group together companies based on a restricted number of industrial sectors. And then as a last step, we produce the RDF. We have a schema, an AIDA schema, and then thanks to this AIDA schema, we produce the RDF that has been published and available for downloads. Now, do you remember the first picture when I showed you Scholarly Data? So that was the paper, all the gray ones. Thanks to this operation, we have been able to add topics. So we know that this paper talks about scholarly data, semantic web, data mining, ontology, digital libraries. We know that, for example, the Open University, it's academic. It's an academic institution. Springer Nature, it's an industry because this colleague of us works at Springer. It's an industry. And we got also the industrial sector, which is it's a publishing company. So we know that this is a collaborative effort paper. Now, the thing is what we can do with it. Okay, of course, this is just one paper. You can imagine that this thing has 14 million papers and 8 million patents, all structured in the same way and all interconnected between each other. So just to spark your imagination in thinking how big is this network, and just to give you a fact, AIDA contains 1 billion facts, so 1 billion triples. So you can imagine how big is this network. So what we can do with it? So the first thing that we did last year was building this approach, which is called research flow. It's a research exercise that we did, which aims at understanding the knowledge flow between academia and industry. So understanding how academia and industry communicate between each other. This is just a use case, just to show to you the potential of this kind of data sets. And because we have papers and patents characterized by topics, and these paper and patents characterized also by academic and industry affiliations, what we can do is just translate the view and get all the topics that have been published in academia through papers, get all the papers that have been published in industry through papers, or patents, topics that have been published in patents in academia, and topics that have been published in patents in industry. So each topic, like knowledge engineering here, can be represented according to 4 signals over time. So there is the papers of academia, which shows to you how many papers this knowledge engineering field has been receiving over time. So in the year 2000, there were published 100 papers in academia in knowledge engineering, while there were only 10 papers in industry and less than 10 patents from both academia and industry. You can see that the patents from industry are growing over time in knowledge engineering compared to the number of papers by industry. So this is just a changed overview over the data, and we can see how topics evolve over time according to these 4 signals. Now, again, what we can do with them. So the first thing that we did, we come up with two indices. First, they are called RP and AI. RP, don't look at the math. It's just a little bit confusing, but follow my words. And those indexes, RP represents whether a topic has been mostly published in research papers or in patents. So if this number is positive, it means that this topic has got a lot of influence in papers. Otherwise, it is if it is negative, it means that is most of interest of is mostly published in patents. If it is exactly 0, it means there is a balance between patents and papers published in a given topic K. AI instead, which does not stand for artificial intelligence, but stands for academic industry, means it's the same of the other one, but basically it's telling us whether a topic is more relevant within academia or industry. So if it is positive, this index is telling us that this paper is mostly interesting within academia. So there are a lot of people in academia from universities that are working on this topic. Otherwise, if this index is negative, it means that this topic is very relevant for the industrial counterpart, which means that it has got the potential of being commercialized, because that's the objective of a company, commercialize stuff. So whether a topic can be commercialized or not. Now, the things that we can do once we devise these two indexes is analyzing all topics. And the first thing that we observed is that these all topics distribute along the B sector of this environment. What you are seeing here is that here you see each dot is a topic, and on the X line you see academia versus industry, and patents. On the Y line you see patents and papers. So if a topic is published mostly in papers, you will find it on the top of this diagram. Otherwise, if a topic is published mostly in patents, you will find it on the bottom of this diagram. And also for academic and industry. Just to give you a brief example, this topic here that I am pointing with my arrow, I hope you can see my arrow, but this topic here, basically it's of interest of academia, has got some interest for industry, because it's not totally here, but it's a bit here. So there are industrial people that are working on it, but it's mostly published in papers. So this analysis can help us in understanding what are the topics that are mostly of interest of academia and are published in papers, and also topics that are of interest of industry and are published in patents. So this can be an interesting insight for people that work in science. Another interesting thing that we can do with this information is understanding how topics evolve over time. And with the same two indices that I showed to you before, rather than computing this index on the overall, on the whole signal, I can split the signals in several parts. So for example, from 2000, 2004, from 2004, 2008, and from 2008, so 2012. And I can see, and 2012, 2016, for example, and I can see how a given topic has been moving around in this diagram. So for example, hand gesture, it was something that started off with an academic topic and published in papers, okay, but then it started becoming more an industrial thing, because industry has been pulling this topic towards its direction, and then it became more a patent topic, a topic that is published mostly in patents. There is encrypted data something that was, at the beginning of the century, published in patents, but now it has become more an academic thing, and because of blockchains and because of other things, and mostly published in papers. The same applies also for smart grids, and instead long-term evolution, which is the LTE protocol, that it's the 4G protocol that we have in our phones. At the beginning, it started with a pure academic and written on paper thing, but then it became, once it became mature, it became like a topic to be patented, and then people can commercialize stuff with it. So this is just one thing. Another thing is forecasting topic impact on industry. So we created a new approach for predicting the impact of topic in industry. So whether a topic will become really relevant in industry, because eventually that is the objective of research, making sure that something becomes appealing for the industry so that it can be commercialized and the whole society can benefit from this technology or this commercialized product. Okay, so the question that you're posing here is, can we predict the impact, whether something is going to become industrial or not? So we use the 4-time series, so publication from academia, publication from industry, patents from academia, and patents from industry. And we tested it on the task of predicting if an emergent research topic will have a significant impact in industry, which means more than 50 patents in the following 10 years. So what we are doing is, I have a topic A, which is emerging today. Will it reach in the next 10 years at least 50 patents in industry? This is the question. So, however, one important exercise is, okay, I can potentially, since I am predicting patents in industry, I can potentially feed in my model patents from industry and see whether it works. However, the goal here is whether the whole 4 signals, so having this fine-grained representation of topics towards these 4 signals can be beneficial for the prediction task. And indeed, we use several models like logistic regression, random forest, ADA-boost, convolutional neural network, and long short-term memory neural networks. And we use several combinations of signals. We initially used research papers in academia, research papers in industry, patent in academia, patent in industry, and then other combination. And from this table, here you see all the 5 approaches. I mean, the LSTM is the one that performs the most, but here what I want to stress is not what is the outperforming approach. What I want you to focus is the fact that if I were to feed patents from industry only, because I am trying to predict patents from industry, and if I feed only patents from industry to predict patents from industry, I will get 75% accuracy, okay, F measure, which is a way of assessing accuracy, more or less. However, instead, if I combined all the 4 signals, research paper from academia, research papers from industry, patents from academia, patents from industry, I managed to get 10% more of accuracy. So this is an interesting result, because being able to characterize topics according to those signals, those very fine-grained signals over time, it allows us to achieve better results. And this is possible only with AIDA, with this characterization of industrial and academic, and also the characterization of topics. So this is the potential. Another thing is analyzing conferences. Okay, so this is another application that we build on top of AIDA, because AIDA contains information about conferences, it contains about information about topics, contains about information about whether we are talking about academia or industry. And this is the conference dashboard that we built. This has the potential to explore conferences on many perspectives, on several perspectives. And this is just the landing page, the overview page of a conference, Neural Information Processing System, which is the NIPS conference, which is the most important conference in neural networks, in machine learning potentially. Okay, and this is the landing page, which allows you to see some or read some general metrics on the left, like period of activity, total publications, total citation, DH5 index, some other metrics, and also the focus areas, like the most relevant, really relevant areas of this conference, because this conference is about neural network, machine learning, and artificial intelligence. Then on the right, you can see some, like a glimpse of what is this conference about. So like how many papers have been published over time, how many citations the papers published in this conference received over time, what are the fingerprint topics by publication and the fingerprint topics by citation. The fingerprint topics compared to the focus area, because eventually they're all topics, but the fingerprint topics is a differently from the focus area, is a more wider set of topics. So they are still focused, but slightly broader, because it's true that this conference talks about neural networks, but also Bayesian network, graph theory, and image processing are topics that are discussed within this conference. Then you can find top authors in the last 10 years and the top organizations in the last 10 years. And as you can see, there are also companies here. There are Google and let me see, Microsoft, and let's see, the rest are all universities. Then we can move towards the citation analysis. So here it's more curated. So we can see the average citation. So what is the average citation that this conference has been receiving over time, and also the impact factor of a conference. Do you remember that at the beginning I mentioned the impact factor that was devised by Eugene Garfield? Typically this is computed for journals. However, the formula is there, and we can apply also to conferences. And the same way we assess journals, we can assess conferences. The impact factor can be a nice metric to assess conferences as well. Then we can rank conferences in the field. So, for example, here what is telling us that NIPS has always been almost the first conference in neural networks, except for some years. Then has been like 4th, 2nd, 6th in machine learning, and in artificial intelligence has been bouncing up and down, because artificial intelligence is a very broad area. So there can be a lot of conferences there that can be better or better than NIPS. Then there is the organizations. Again, we can see the organization according to publications and citation. On the left, the publication, on the right, the citations, and we can see how many publications. And I mean, this is a pretty static view, but this is pretty customizable. You can move to a time-based view. You can choose whether you want to see only academic institutions or industrial institutions. So by click on industry, it will remove all university. You will see only companies, and you can enlarge the analysis from just the last 5 years to the last 10 years, or the whole period of time that this conference has been operating. The same applies for the citations. So this gives an opportunity for all people that want to analyze conferences and make sure that this conference runs good, or assess the conference. And this is a way for doing that. Another way of assessing conferences through the countries. What are the most prolific countries? Okay, so we can see that United States and China have been playing a key role. Actually, also Canada and Europe, United Kingdom, Germany, and France have been playing a key role in this conference. And then you can see that there are some other countries that tend to not publish too much. Now, Africa, it's a continent that is white in most conferences, because Africa is a special case. Doesn't have that much funding, that much resources to pursue research. So there are some countries that in terms of research are going strong. However, there is a lot of work. So policymakers can take this as an interesting insight to fund more research and to make research more equal throughout the world, throughout the entire globe. Then there is also topics. You know, there are all topics. Here you can see all topics, and if you switch to fingerprint topic, you will observe all topics. I will just go quickly through this because at some point it can become quite cumbersome. Then there are the authors, which can be assessed through publication and citation, and according to the H index, and H5 index. And then there is the related conference. This is an interesting aspect because we can compare conferences. I mean, imagine I am a student and I know only one conference in one field, and I want to understand, okay, what are the other conferences that are really good in this field, or perhaps better? Now this does NIPS, okay, it's the best one, but imagine I was observing another conference and then that was like the 4th place, and I would choose to publish at another conference that is better of that conference. Through this rank, I could easily see what are the best conferences in that field. And here we can see this is an interesting thing, because other dashboards, because the world is full of dashboards, okay, and this is one way in which we differentiate from the others, and we can analyze industry as well, okay. So we have a way of characterizing whether publications or citation are more in academia or collaborative efforts or industry. And we can also see this distributed to industrial sectors. Yes, I have that slide. So for example, I have that in this conference, there are mostly companies from technology, computing and IT, electronics, and just a few of them in automotive and transportation, lighting, and so on. Now, let's get our hands dirty. Just one thing, other questions. I mean, this is basically what we can do with this. Are just few cases of what we can do with AIDA. So AIDA, being integrated with a lot of additional information, supports all sorts of high-level applications like the conference dashboard or the research flow that I've been showing to you. And but there is potentially a lot of other things that we can do, and which are future work. So I was wondering, does any one of you have questions for me at this stage before we get into the practical aspect of this lecture? In the meantime, I'm going to sip some water.
So if you have any questions, please type them, or feel free to raise your hand and just talk. Otherwise, we can proceed to the practical part.
Yeah,
and,
sure.
See if there are questions there.
Yeah, the only problem is that I don't see the chat. I don't know why. Maybe because I'm not from the same institution of yours.
Okay, don't worry. So I will.
Okay, cool.
Check it and see if there are any questions raised.
Okay.
I will moderate.
Perfect. So I will move on. Okay, I've got exactly 40. It's like I have 40 minutes, right?
So you can, yeah. So you can have as much as little time as you want. So.
But I'm talking about the poor students that are listening to me, so they won't escape. Anyway, I will try to stick with the time. I mean, I'm not going to take 40 minutes. I'm sure about it, but just to be
half
sure.
An hour would be okay.
Okay.
Thank you.
So let's get our hands dirty. Okay, we are going to practice a little bit today with something that I call AIDA 35K. It's similar to AIDA, but not so similar to AIDA. because, for example, whether because it has got some additional information and some information has been taken away. So it's a differently shaped version of AIDA. And this is the schema. So again, at the center of everything, there is the paper. And then there is the author. And all these entities are connected to other entities or literals, because of course, as type is a literal here, industrial sector is a literal here. It's not an entity in this data set. You can download, I don't know, Dimitris, did you send them the tutorial I sent to you?
So no, I haven't done this, so I leave it for the assignment. So let me just make a pause here and say that the fourth assignment will be on this data set. So please pay close attention to what you hear now.
Yes, pay attention. And yes, so the dataset can be downloaded from this URL, but don't worry, you will receive all the material and everything. So you don't have to quickly type it now, so before you lose the page and you lose forever the URL to download the dataset. Don't worry. So just look at this this schema here. Okay. This is just a graphical representation of the schema, but let's get into the actual relationships and the actual entities. So again, there are papers and authors, and then there are other things like the CSO topics, the industrial sectors, and so on. But anyway, let me dive. What does this dataset include? It contains 35,000 papers in the field of semantic web and neural networks. It contains almost 250 facts, 250,000 facts, so triples, and there are 26 different relationships. So all these relationships, all these links that you see here are basically, I don't see why my mouse goes wild. Okay, now it's better. Okay, those are the old relationships, the 26 unique relationships. And this is the full list, but I will just spend a few slides in explaining them, because I want you to understand exactly what this dataset contains in terms of facts. So the simple one starts from paper. So the paper is the subject, then there are these relationships here, and has got some objects. So there are the first relationship is as author, which states the author of the paper. Then there is as conference name and as conference series, which provides details about the conference. So, for example, the 21st World Wide Web Conference and the WebConf. So conf name is 21st World Wide Web Conference, and WebConf is the conference series. So basically, what are these? One is the full title, and the other one is the acronym. So conf name is the full title of a conference, and conf series is the acronym. Then there is as CSO enhanced topic. It's a topic extracted with the CSO classifier. Then there is as entity type, which defines the type of document. In this case is paper. Is always paper, because in this dataset there are only paper. Then there is as journal name, which states the name of the journal. And just to give you a little bit of understanding, a paper can be published either in a conference or a journal. So if a paper has got a journal, it doesn't have conferences. It is also true the vice versa. If it is published in conferences, it doesn't have information about journal. So this is to say that it's true that this dataset has got 26 relationships, but it's not true that all papers will have always the 26 relationships, because some papers can be different between each other. So then there is as reference, which points to all referenced papers, because I don't know whether you are familiar, but a research document, at the end of a research document, you put references, you put citations, you reference someone else, because perhaps what you have been describing is part of another person's work. So you say, okay, this work comes from this person, and you write it at the end. And those are counted as references. And actually, I think in your assignment, you should have also you should put also references, as far as I know. But so that is the same. So a paper has got references. So it's a way of connecting paper to each other because they reference each other. As type defines whether a paper is in academia, industry, or collaborative. So whether a paper has been written by academic authors, or whether it's been written by researchers working in industry, or whether it's a collaborative, like the paper that I showed to you in the example. If that paper is written by industry people, then there will be industrial sector. So you will see what are the industrial sectors of that paper. As year states the publishing year of that paper. So if my paper has been published in 2019, you will see as year 2019. Now, there are additional relationships always also from paper that instead have got a little bit of reification. I will show to you an example of it so you don't get confused. So for example, the paper can be connected to a distribution of affiliation through as affiliation distribution. And each node of this distribution has got as affiliation and the as affiliation weight. So as affiliation describes the affiliation of authors. The object of this relationship is another statement, reified object. So the as affiliation distribution points to another fact. And this reified object then contains as affiliation and as affiliation weight, which identify the affiliation of the paper and the percentage of authors belonging to that affiliation. Now, there is an example just because I don't want you to get confused by it. So just to better understand reification, imagine there are three authors, me, Angelo, Francesco from the Open University, and Dimitris from the Université Libre de Bruxelles, who co-author a paper. We are together writing a paper, all the three of us from the university and so on. So here there is the RDF version of that paper. So there is the entity type of paper, there are the authors, which are entities, me, Francesco, and Dimitris. Then there is affiliation, the Open University, as affiliation, Université Libre de Bruxelles. However, we want to understand what is the weight of a given university. So we associate as weight 0.66 to, because there are two people coming from the Open University, so the Open University has more weight, so 0.66. And the University of the Bruxelles has got 0.33 because there is only one person out of three working in this university. However, if I were to structure my RDF statements as is in this way, it will be quite hard for me to tell what is 0.66 referring to, or what is 0.33 referring to. Is it to the Université Libre de Bruxelles or the Open University? So you see that I am stating facts, but I am being very ambiguous. So there is no way a machine can interpret this very in a proper way. So one way of doing this is through reification. So imagine again the same problem. There is Angelo, Francesco, and Dimitris, and but now I have a better version of this triple. So I go to as affiliation distribution, then I create an object, a reified object that contains a statement. So I create affiliation distribution paper ID affiliation, so it's a combination, this one, and then this subject has got as affiliation the Open University and as weight 0.66. So now an automatic machine can easily tell whether 0.66 is belonging to the Open University and whether 0.3 belongs to the Université Libre de Bruxelles. So by creating this let's call it fakery object, but it's not fake, it's a proper object, okay, like a proper entity into the network. We are able to say that this paper has this fact, as affiliation distribution, has this fact, and this fact is that there is the Open University as affiliation, and the weight of this affiliation is 0.66. So this is the whole point of reification. And the same applies to citation distribution, as country distribution, and as grid type distribution. So as citation distribution describes the received citation. So whether the number of so describe the citations, and the as citation here is telling me how many citation I have been, what is the year? I'm getting a little bit confused. Let's do one step back. So there are a similar relationships like that use reification, which are as citation distribution, as country distribution, and as grid type distribution. Then what happens is that the citation distribution, what it does, it describes distribution of citation that a paper has received each year according to a weight. So in this distribution, we'll find, given a paper, you will find a year, the year in which it was cited, and a weight on the amount of times it was cited. The same is for the country distribution, describes the country of the affiliations. So, for example, it's like the affiliation distribution. Basically, it's saying the country and what is the weight. So, for example, in my exercise that I showed to you before, there will be United Kingdom 0.66 because from European University is the United Kingdom. So United Kingdom will be connected with 0.66. Instead, Université Libre de Bruxelles, because it's in Belgium, it's a country that will receive the weight of 0.33. So it's the same of affiliation, but instead of having the name of the university or the name of the industry, we have the country. And the grid type is the same. Has got a grid type that it can be education, industry, government, healthcare, non-profit, and so on, and you have a weight. So, for example, in that exercise that I showed to you before, both Université Libre de Bruxelles and the Open University are academic institutions. So, as a grid type of that paper, there will be only one entity, which is academia, and it will have full weight because both of our university come from academia. So this data set help us organize the information of the countries through this reification. We are able to organize the information about the countries, the affiliation, and the citation distribution, and also the grid type, whether we come from academia or industry. Because, for example, a paper can be collaborative, but how collaborative is that? Okay, it can be that it's collaborative with 50% academia or 50% industry, or it can be a different balance. So it can be like 90% academia and 10% industry. So this is a good way of representing how the collaborative effort is ruled for that paper. Now, there are also relationships that come out from authors, and there are only 3 relationships, and 2 of them are also reification. There is as paper, so this is a way of connecting back, because from paper there is as author that connects papers to authors, but there is also author as paper, so it's a way of connecting back the author from the paper. It's a little bit redundant because in RDF you can always switch back in Sparkle, sorry, when you and you can also infer it. I mean, if you have a schema that says that if a paper has author, that author, you can say that that relation is the opposite of author as paper. In that way, if you have an inference machine, it will infer the same relationships. So you don't have to state them. This is the nice thing of RDF, because you can put statements and then you can run an inference machine that will infer all the possible relationships that come out from this data set. So if you put paper as author, and then the author, and you write in your schema that also the opposite relationship is true, then when you run this inference machine, it will extract also all other facts that says this author has paper. But we included them anyway, so it's fine, just to avoid confusion. Then has got there is as network in distribution, which is exactly the same as affiliation distribution, and as worked in distribution, which is the same as country distribution. Sorry. So I hope I didn't confuse you too much, but let me go 1 second here, so that okay. So from the paper, you have a citation distribution, which contains the year, and it contains also the weight. So it means how many times, what is the weight of how many times this paper has been cited in this year. So the country distribution, you see the country, and then you get the weight. Then you see the affiliation, you get the affiliation, so the Open University or Université Libre de Bruxelles, you get the weight 0.66 or 0.33, and you can see also the grid type distribution, academia or industry, and their weight. And you can see also that, for example, the as network distribution and as worked in distribution leads to the same distribution of the paper. So these two entities have got as a range, as a domain, both author and paper. And remember this, because it's going to be useful for you for the assignment. And okay, how do we interact with such data? Okay, I've got like 20 minutes for that. So setting up a triple store, how we deal, because the data comes within its format. You can download it. It's most likely in RDF. Yeah, it's definitely in RDF, but most likely in TTL format or in other formats that are RDF compliant, because there are several formats out there like N3, Turtle, XML, JSON-LD. There are many formats. But how do we work with this data? I mean, do we have to develop algorithms that go through this data set and does the queries for us? The question is no, we don't have to do that, because there are a lot of datasets that do that for us. And one of them, I mean, some of them are GraphDB, Gina, Apache Gina, BlazeGraph, Virtuoso from OpenLink, Stardog, and AllegroGraph. And today we are going to use GraphDB. So how does it work? You download it and you install it. Of course, it comes with a license, in the sense that you have the free version. Of course, you can download the free version, which you can use it. There is no trial. You can use it, but you have a limit in terms of what kind of functionalities you can run. But don't worry, because you certainly can load a dataset and you can run Spark queries with it. So you don't have to pay for it. At least for the free version. If you want more complex thing, you have to pay. But this is not the case. So the first thing that you have to do once you install and run GraphDB, GraphDB runs in a browser. Technically, it's a Java application. So you download, you install it. It runs a Java daemon that will open a browser page. So you will interact with this dataset through the browser. So you go into a repository, you create a repository, because you can have multiple repositories on this GraphDB app. And once you create the repository, you load the dataset. So you load the dataset you will download, and you will import it. It's going to take around 2 to 5 minutes. It depends on how fast your machine is. Then you select the, no, this has to be done before. You select which repository is that, and then you go straight away to Sparkle, and you write your Sparkle queries, and you run them. Now, this is more fun, because eventually we get to get our hands dirty, literally dirty. So the first Sparkle query that I want to show is describe. Describe is it's a substitute of select, but it allows to describe the whole entity. So what it does is, if you think about an entity like positioned in a network, and then it has got all the, remember that the RDF or scientific knowledge graph or knowledge graph in general are directed, is a directed graph. So there are outlinks and inlinks. So this describe feature of Sparkle, it lists all outgoing and ingoing links. So to show exactly, given an entity, to what exactly it is connected, what are the outer link and the link that are coming in. So then there is select papers by year. So it's pretty straightforward. Use describe and you put the entity URL. You can use this. You can use the. You can either write the URL or URI like full. You can write the full URI, or you can use these prefixes like AIDA 35K, which is a prefix. So every time there is AIDA 35K, is going to refer to this. Those are kind of called syntactic sugars, a way of shortening your syntax and make it more legible, like you can read it quite easily. It's very easy to read that you are describing an entity that belongs to this URI. It's a resource. Then if we want to select papers by year, imagine I have a year like 2010, okay, and I want to select all papers that have got all subjects, so in this case papers, because as I mentioned to you, there is a relationship between the year and the paper, which is as year, and you can use this prefix AIDA 35 key schema, which is different from this one, okay, which is different from this one. So you can get all subjects that have got like that have been published in 2010. Of course, we don't know exactly how much or how many, sorry, this paper will be, so we can limit this to 100 because it can take time to imagine we have 1 million papers. Okay, it can take a lot of time for GraphDB not only to retrieve this large amount of data, 1 million papers published in 2010, but also to print them, because the printing has its own cost. So you have to structure in a table and so on. Actually, let me let me see if I can do this. No, I cannot do that. Okay, just a second. I want you to give Okay, Dimitris, can you tell me if you see the GraphDB page?
Yeah, perfectly.
Okay, perfect. Okay, you go. I already loaded. I already run the GraphDB. As you can see, it's my Opera. It's a browser. It runs on localhost because there is a JavaScript, Java, sorry, not JavaScript, because they are two different things. It runs in a browser. So I already loaded the dataset. I am in my repository in AIDA 35K. So what was the query? Get by year. Yeah, this one. So I am extracting all subjects and I can run it. So here I am getting all papers that have been published. One thing that I can do certainly is, let me check if I can do this. For example, when I don't know, I can count as count. I think it should work like this. No.
Maybe you need
yeah,
more parentheses.
Yeah. Sorry. Get by here. Yeah. Of course, Sparkle is confused. Doesn't know. So, for example, if I don't, of course, in this case, limit, I don't need it anymore because it's gonna give me just one number. So it's telling me that, for example, there are 178 papers that have been published in 2010. So in case we don't know, and then in that case, we know that is a fairly good number, manageable. So we can, for example, remove the limit, and it's going to return to us all 178 papers, which are listed here. Yes, 178 papers. So those are all the papers in this dataset that have been published in 2010. Then what was there? Okay, then there is identify types. So the type is whether a paper has been published. So it identifies, okay, it identifies the distinct of, let me do one step back. Given a paper, you know that as type tells us whether a paper has been published in academia, industry, or it's a collaborative. However, here what we are extracting is the distinct of those objects. So it's going to tell us the unique types that are available in our dataset. So it's going to tell us how many are there, because so far I've been mentioning that there is academia, industry, and collaborative. But first, there can be more, although there aren't, but there can be, in a larger dataset, there can be more, because, for example, there are papers written by governments. And secondly, we might want to know how exactly those labels are written. Is it collab or collaborative? Is it academia or academic? Industry or industrial? We don't know. So this is a way to identify the types within the dataset. So if I go back here, type, yep. Actually, the limit is useless in this case because we know there are just a bunch of it. So we know that there are three types: academia, collaborative, and industry. Then let's go to the next slide. Okay, now that we know exactly how industry is written, academia is written, we can get all papers and their affiliations that get paper and the affiliation that come from industry. How does it work? Given a subject, I extract all papers that have got type of industry. Then we go into the affiliation distribution. Remember the reified object. Reified object is here. And then the same object, we get the affiliation. So this Sparkle query is going to match the triple pattern that fulfill, it's going to match all the subjects and objects that fulfill this triple pattern. I'm going to run it for you. Get all companies. Perfect, this one. So what we are seeing here is that there is this paper that has been written by Portugal. I mean, eventually I can hide this reification object. I don't need it. So I can do S and then O, not 0, O. So I simplify my view. So I see that this paper has been written by IBM, Siemens, Intel, Verizon. So I get to see, well, what are the company? There are just few of them eventually. There are not all of them, but what I can do is to get all companies, I can get distinct, or to get what are unique companies. So I can see that in my dataset there is the BT group, BT Research, Tata, which is a company car, Accenture, Google, Cisco, and this is just to give you an example of the potential of these queries. The same applies also for academia, so we can do the same for academia to understand what are the affiliations that the main affiliations in academia. Where is it? Here, academia. So the same query, of course, but here we put a limit because there are more academic institutions. Actually, let's count them again. Let's not do the mistake of before. Count. I have to do distinct. As count. This should work. I can remove this. So there are, sorry about that, 425 unique universities in this dataset. If I remove distinct, let me check how many of them. Yeah, almost 2,000 universities. So as you can see, again, I start from the subject, a given paper, because what I want is affiliations. I start from the paper, and I get that this paper is from academia, and then I get the distribution. I get the reified object, so distribution of those papers, and then I get the affiliation. It's the same as industrial, the same thing. Then I can get all the papers that have been written by Carnegie Mellon University. And so let me go here, Carnegie Mellon University. How does it work? So again, given a paper, what I want are all the papers. So I want all the papers. So select subjects. This subject for me is a paper that has got as an affiliation, again, the reified object, and affiliation distribution, and then this affiliation distribution has got Carnegie Mellon University. So in this way, I get to extract all papers that have been published, that this university has been publishing. Let's go ahead. The same applies for United States. Here we are going to use a different distribution, not affiliation distribution, but country distribution. Here we want to count the papers. So let me get back. USA. So again, I count, and I get objects in country distribution. I get the papers that have got a country distribution, which country distribution as country United States. And I count that there are 349 papers that have got affiliation in the United States. What else? Let me check. I've got another 2 slides. Okay. Then I can count the citation of a paper. This is an interesting one because this is perhaps one of the most used one, because people, to assess science, use a lot of citations, and they count citation. So in AIDA, I have a paper that cites another. So to get how many times my paper got cited, I have to be the object, because I received the citation. I have to be the object, and I have to get all the subjects that cite me. Okay, they make a reference to me. So this is why I count all the subjects, okay, that reference my paper. For example, of course, this is not my paper, just paper for the sake of the example. So what is it here? Count citation. So you can see that there is this paper which received 3 citations. If I don't want to count anymore, but I want to know exactly who cites me, what are the papers that are citing me? Because, for example, I want to see how my paper is cited. Is it cited because my work is good, or because my work is bad? So they're talking bad about me, or they're talking good about me. So I want to know who is citing me, and then in this case I can do this. I can simply remove this space, run. So those are the 3 papers that cite me. And actually, if I go into this resource, okay, I need to remember this. I want to see whether I find it. Okay, this is the way of seeing an entity. So you see all the paper, and then you see all the relationship. And I want to see if my paper is there. Yep, it's here. So you see that my paper, this paper, references my paper here. So you can see other things. So this is a nice way of exploring the dataset as well. Of course, you have also the the scribe, which allows you to see all the relationships as well. You see all topics and so on. Let me get back to the track. Count papers of a topic. Okay, so we want to understand also, for example, for the sake, because I don't know, I'm interested in trends. I want to see how many papers have been published in the field of World Wide Web, or I don't know, artificial intelligence, or any kind of topic. So I want to count them because, for example, I want to rank them. I want to rank topics. I want to see who is the most published topic. Okay, so one way of doing this is certainly counting the paper that a given topic has received. And let me get to the thing. Okay, count topic. So why I don't see? Let me run this. Okay, now I see better. Okay, again, so now I'm counting all papers. So I'm counting all subject papers that have got CSO and answer topic World Wide Web. Okay, I've got that more than 2,000 papers talk about World Wide Web. In this case, I'm interested in about artificial intelligence. So I know that artificial intelligence is written by like this because I designed the dataset, so I know. But if you want to know exactly what is the unique set of topics, you can run. I'm not going to do it, but you can think of running a query that does the distinct of all the topics that are in CSO and as a topic. For example, you get all papers, and then you do the distinct, as I showed to you in several other cases. So running artificial intelligence, it has got 1,400. So you can see that World Wide Web is stronger than artificial intelligence. So this is a way of classifying things or getting trends. Then, last two, get the journal containing the word semantic. Now, this is a slightly complex query because it's true that in AIDA we have a given paper and we have also the journal it has been published to. We know exactly. But however, the name of the journal can be very long. Okay, so actually I'm gonna run this for the sake of an example. Journals. Okay, so I'm gonna remove this and run this. So you can see all the list of journals that are here: Journal of Biomedical Informatics, PMC Bioinformatics, Springer International Publishing, ACN Transactional Internet Technology, Journal on Data Semantics. You can see a lot of them. But in this case, I am interested in getting all the journals that, for example, contain the word semantic, because, for example, I work in the field of semantic web, and I want to publish something that is about semantics. So, okay, I want to find the journals. And how does it work? Because this journal name are too much, first of all, and secondly, are too long. I don't want to parse all of them. So what I can do, I can filter the name of the journal containing, so if the string O, the name of the journal, contains the semantic web. So in these filters allows us to retain all those objects, so the journals that contain the word semantics. So what we do is that we have 6 journals. So this is much easier now to parse. Okay, there is the journal of web semantics, biomedical semantics, data semantics, semantic web, and so on. So I can see exactly which kind of journal I can possibly send my paper to. And the last one, actually those are 2 queries, but it's the ask construct, which like describe substitutes the select. So the ask, it's a construct in Sparkle that allows us to get a yes/no answer. It doesn't return a graph, or it doesn't return a list of triples. It returns are true or false. So in this query, what I am showing is whether there are papers that have been published at the conference dub. Okay, there is a conference that has got as an acronym the www, and I want to know whether there are papers there. Let me check if I have this query. Yes, I have it. So, okay, because this is a strict paper. Yes, okay. So there is a yes. So there are papers. What it's telling us is there are papers there that have been published at dub. If I write this, for example, now dub.s does not exist. I don't think it exists. So there is no triple matching this triple pattern. And indeed there isn't, because dub.s does not exist. So not only does not exist, but there are no subjects connected to this conference. Now, how about we put a paper that has been published to this conference for real? I want to see, is this paper published to dub? This is a question that I'm asking. In this case, interesting. What is the code? It should say yes. 1566. Yes, it's no. Sorry, I'm getting confused. Of course it's a no, because before it was a yes, and now it's no. Yeah, this example was on purpose made for answering no. So I can potentially get, let me check, a paper in a conference. Okay, select star where, in this case, I take this, no, take this, I run, I get a paper to see whether this paper has been published, and then I transform this in ask, and then I put this here. Now I'm asking, is this paper published at dub? I know it because I selected it from dub. It's gonna tell us yes. So the paper before was not published because I made on purpose to not be published at dub. So this is everything from my side. This was the last query I wanted to show to you, and I want to I'm done. This is finished, and I want to take this opportunity to thank all my colleagues from the same university and from the University of Cagliari that we worked together to build this data set. I mean, the AIDA 35K is just a toy project that we designed for a little experiment that we were doing in collaboration with the University of Bonn. And this is everything from my side.
Okay, thank you very much. So just to continue from where you left off, so you saw I guess the students saw some interesting queries, Sparkle queries on AIDA 35K. So for the assignment, you are going to build some queries and a bit more complex queries than the ones you saw. But this is, at least you got a picture of how you can think of making queries on this data set. So just to say that the assignment will be, and the instructions for the assignment, so you will install Graph DB and download the turtle triples and install them and play with them. So they will come later today. So just let me see if you have any questions for Angelo. Anything that you would like to ask regarding scientific knowledge graphs in general, about AIDA more specifically. So I have just one question I would like to know. So can you tell us what are you currently working on with AIDA? Was it, I think I saw somewhere, link prediction. So what are you trying to predict? What that means?
Yes. Okay. So actually, the AIDA 35 has been built as a reduction, a small data set for this link prediction exercise. Okay, the link prediction, because what happens is that I mentioned to you several times at the beginning of this lecture that the data sets are sometimes incomplete because the information is not available, or sometimes is not accurate. So one exercise, because of this, we need to come up with smart ways of coping with this mistake, coping with these errors. How do we deal with these errors? So one way that the literature, or actually the research community, has been responding, not in the scholarly field, but in other knowledge graphs, is by link prediction. So do you remember the, okay, I will share quickly my screen again. This one. Perfect. Okay, so do you remember okay, this, I have to go very, very far. Okay, I want to stop here for a second. So one way of the community, has responded to this issue is building knowledge graph embeddings. So here I show to you word embedding model. So how does it work? It takes the text and it associates for each word an array of numbers. However, the knowledge graph embedding, it takes the entities and relationships and does the same process. So instead of having king here, I will have like I'm typing this, but then I will change it back. For example, I will have https://skg.org/resource/Angelo Salatino. And so each node then will be associated to an array of numbers. And what happens is that instead of having this model here, that male, female, web tense, country capital, it will have nodes, entities, and relationships of a knowledge graph. So thanks to this trick, what we can do is, given that king is here, and man is here, and woman is here, can we infer a relationship between king and queen? So this is the objective of link prediction. Now, how this is projected to our exercise, our SKG thing, is because data is often incomplete. So for example, grid information like education. So from grid, we were inferring whether a paper was coming from education, industry, or academia, or collaborative effort, and so on. So one way of that has been trying to be able to see whether we can somehow, even if the information is not available, try to say that paper is academic, that paper is industrial. So completing the information, because the gridded information is not always available for two reasons. The first reason is because grid ID is a dataset that is manually curated. So there are people that assign an ID to each university. So the Université Libre de Bruxelles, this ID, what is it? Here. This ID that Université Libre de Bruxelles has, let me make it larger. It's been manually assigned. So there was a person that gave this number. So you can imagine this effort takes a lot of time in assigning all companies and all universities that publish. Of course, at the end, it's going to receive like a plateau because the number of new universities that's going to emerge is very low. It's possible that there will be emerge new university every day. So it's about adding adding existing university. That's it. The reason why I get to this was the first motivation. The first is that grid does not exist for each institution. Doesn't exist. Academic is industries. Not all industries have got a grid ID, because, for example, there can be a company in London that is very small, but because he has done something nice, he has published it, but it doesn't have a grid ID yet because it's just new in this space, so it doesn't have an ID. So for us, it's kind of hard to tell that. First of all, this is a company, and second of all, do all these kind of things, and the second problem is that it's true that from the papers we are able to extract affiliations, but sometimes it's very hard to connect affiliations with the existing grid ID, because there is a process. I found this paper that talks about that is written by Angelo at the Open University. However, I need to set up a pipeline, an algorithm that given the string Open University, that can come in several ways: Open University, the Open University, knowledge media at the Open University. So there can be several ways. I need to set up a pipeline, an algorithm that, given all these possible strings, is able to connect to the grid ID of the university. So this is the second problem. So those are the main two problems of why the grid ID information can be missing in the dataset. So one way of one exercise has been link predicting and predicting whether a paper can be a company or academia, because the grid ID is not available, simply because of that. Sorry, I took it too long, but I wanted to give the full explanation of it.
No, thank you. So this is very clear. So you want to infer
exactly
by means of machine learning relationships that are missing or you cannot identify in your pipeline.
And this is done via knowledge graph embedding. So each node gets its numerical representation, and because they navigate in this space, what is it? It's here. They navigate in this space, in this n-dimensional space. I can easily check whether two nodes are close to each other. And of course, the difficulty is in training this model, because each model is going to create its own representation that can be really different. So one node that can be really related can be far off, or so depending on the domain, there can be a lot of solutions in building knowledge graph embeddings.
Okay, yeah, so yeah, that is clear. Okay, so I think we should probably end because we're a bit over time. Thank you very much for your very interesting presentation, first on the topic of scientific knowledge graphs, and second on a specific scientific knowledge graph. and for doing all the queries, Sparkle queries. That was very, very interesting, and for sharing creating this data that we can use for the assignment.
Yes.
So thank you very much for your overall contribution. I'm personally very happy to have you. So let's stop here. Thank you. So let me stop the recording. Thanks.